Now I will explain what is plane transmission grating. A plane transmission grating is a 1-inch glass plate on which, by using a diamond pen, we can draw as many as lines on that plane transmission grating. We have taken a plane transmission grating which has 15,000 lines per inch. So the apparatus required for this experiment is a spectrometer and a mercury light source and a magnifying lens. Mercury light source, if we talk, a mercury light source consists of 7 wavelengths starting from violet and it ends up to red. The highest wavelength is of red and the highest frequency is of violet, as the frequency and the wavelength has an inverse relationship. So the formula used to calculate the wavelength of these spectral lines is A plus B sin theta is equal to n lambda. Here we need to determine the wavelength of these mercury source spectral lines. So from this relation lambda, I can define it as A plus B sin theta upon n. The denominator term n represents the order of the diffraction grating. The order of the diffraction grating in this experiment we have kept as 1, not 0, not 2, because if we go on increasing the order of the spectrum in the diffraction grating, so in that turn the spectral lines will be obtained, but that intensity of the spectral lines will go on fading or it will go on reducing. So we always prefer n equal to 1 order. So in this one, this is n equal to 1 order. Now we come towards the numerator part. In the numerator part, we have 2 terms. One is A plus B and second is the sin theta. So first I will explain what is A plus B. A plus B, we normally call it as a grating element. Now grating element A plus B can be calculated by using a formula that is 2.54 upon n. Now what is 2.54? If I draw diagrammatically this plane transmission grating, so this plane transmission grating consists of these lines and this distance is 1 inch. So if I convert 1 inch into centimeter, it will be 2.54 centimeter, and upon capital N is the number of lines lying on this plane transmission grating. So in our experiment, the value of capital N is 15,000 lines. Clear? Why we are converting the inch into centimeter? Because we need to calculate the wavelength, and wavelength we always represent in terms of centimeter or meter or nanometer or angstrom. That's why we will convert the inch into centimeter. So 2.54 centimeter upon n. So capital N we know, this value we know, so automatically we can calculate the value of A plus B. Now we come towards, in the experiment, the basic term is least count. So what is least count? We normally call least count as the value of one division on main scale divided by total number of divisions on vernier scale. So here I am representing a small diagram where I can explain you what is vernier scale and what is main scale and how to calculate a least count. So if we have 2 readings over here, that is the upper topmost layer, this is my vernier scale division. So vernier scale division, if I see from 0 to 30, it has 30 lines over here. Diagrammatically you won't see the 30 lines, but it consists of 30 lines, that is my total number of division on vernier scale is total 30. Now we will move towards the numerator part, that is the value of one division on main scale, how we will calculate the main scale. So in order to calculate main scale, we have a spectrometer, that is a prism table. The prism table consists of total 360 degree rotation. So I have not shown here complete 360 degree rotation. I have shown here a very small part of it, that is 10 degree to 20 degree. So from 10 to 20 degree, if I see here, it consists of nearly 20 divisions. 20 division means this longer line smaller. If I calculate 1, 2, 3, 4, 5, 6 until here, it consists of 20 divisions. That means in 10 degrees, I have total 20 divisions. So what is the value of 1 degree? That is equal to 20 divisions divided by 10, that is 2. So what I will do, the value of 1 division on the main scale is 2 divided by total number of divisions, that is 30. Sorry, I will recorrect it. So I will calculate the total number of divisions on vernier scale. So here in the diagram, this is my topmost layer, which is a vernier scale. So total number of division on the vernier scale is 30. Now I will calculate what is the value of 1 division on the main scale. So in order to calculate the main scale, we know that the spectrometer has a complete 360 degree rotation, which I have not shown it over here. I have explained only to a very small region of that is from 10 degree to 20 degree. So from 10 to 20 degree, we have nearly, if I calculate or if I count it, it has nearly 20 divisions. That is 20 divisions is equal to 10 degree. So what will be the value of 1 division? 1 division will be 10 divided by 20, which is equal to half, that is equal to 0.5. So the value of 1 division on the main scale is 0.5 degree divided by total number of division on vernier scale, that is 30. So in this way, we can calculate the least count of a spectrometer which is used in our experiment, that is wavelength of spectral lines. Now this was a calculative part for calculating the least count part. Now how I am going to take the readings over here and complete calculation. So what I will do, we will plot a table. In this table, here is my order of spectrum. Then comes my which color I will choose over here because it has 7 colors. Then comes my readings on right hand side. Readings on right hand side. Then comes my readings on left hand side. And for right hand side, I have to divide this column in 3 parts. That will be my main scale reading, then vernier scale reading, then total. That will be my, I will denote it by A. Same thing, I will do it for the left hand side. I will divide this column into 3 parts. Again, I will write main scale reading, then vernier scale reading, then it is my total B. Then we have more columns over here. That is 2 theta, which is equal to A difference B, then it is theta, then we have the final mean theta. Order of a spectrum, as I said in order of spectrum, I will take 1 because at n equal to 0, I will get complete white light which consists of all the 7 wavelengths. I need to get the value of individual colors, so I will take the order of a spectrum as n equal to 1. Color, I will just choose the starting color, that is the violet. Now what I will do, reading on the right hand side, main scale reading. So now in order to calculate the main scale reading, what we are doing in the experiment, where the vernier scale, the 0 of the vernier scale, if it coincides with any divisions of the main scale, if the 0 of the vernier scale coincides with any division of vernier scale, any division of main scale, that gives me the main scale reading. For example, if I take the main scale reading as something 180 degree. Now comes vernier scale part, as I have shown right now in the previous part. Vernier scale, it consists of 30 division. From the 30 division, 0 already coincides with the main scale division, that is my this reading. Now left over 29 division, now we have to check using the magnifying lens. The rest 29 division, there would be any one division which will coincide exactly with the main scale reading, that means they will overlap. That division we have to write it as vernier scale. If I write, that is my 15th division. So how I will write my total A? So in order to write down the total A, that is total A, I can write it as, always we write it as main scale reading plus vernier scale reading into my least count. So this, by using this method, we will write down the value of total A over here. That is my main scale is 180 degree, vernier scale is my 15th division, and my least count I was getting it 0.5 divided by 30, that is nothing, 1 by 60. Okay, in this way I will write my total A over here. This I had done reading on a right hand side, that is I will move my telescope towards the right and I will stick it on the violet color. Now I will bring back my telescope to the center and then I will turn it towards the left hand side. Again I will note down my main scale reading. For example, it is something 360 degree. Then vernier scale something 20 division, and then I will write down the reading of my total B. This is my wallet and this is the reading of V1 window, and same way I will write down the reading for my V2 window, because in the experiment we have two windows, V1 and V2. So I will note down the readings of V1 of main scale and vernier scale. Parallelly after that I will write down the readings of V2, that is this part. So here for the right hand side I will note down the reading, for the left hand side I will note down the reading. Then we will calculate 2 theta, that is the A difference B. Here it is A difference B, there is no negative sign over here. Difference means that we have to subtract the higher values from the higher values, we have to subtract the lower one. So I will get the value of 2 theta over here, that is A I have it over here, B I have it over here. So I will get 2 theta over here, I will get 2 theta over here. Then I will calculate theta. I can easily get the value of theta, what it is, whatever value if I am getting over here. For example, I am getting 36 and here I am getting something 34. So my theta will be 36 divided by 2, that is something 18, 34 divided by 2, that is something 17 degree. So mean theta, I can calculate easily mean theta, that is 18 degree plus 17 degree divided by 2, that is something I will get 35 divided by 2, that is something 17.5 degree. This 17.5 degree is the value of theta for my violet color. Then for the calculation, finally we have reached towards the end of this calculative part. I have already mentioned here, lambda is given as my A plus B sine theta upon small n. A plus B I have already explained, it is my grating element which we can calculate as 2.54 divided by capital N. Capital N I already know it is 15,000. Now comes sine theta, which is very important parameter over here. Theta I am getting for violet, it is 17.5. So my A plus B into sine 17.5 degree divided by n, that is 1. I will get the value of lambda, which is for my violet color. So similarly I can calculate for violet, I can calculate for indigo, blue, yellow, orange, red, any color which we want to calculate. Right now in this experiment we are going to calculate for 3 colors, that is for violet, and second I will choose for the yellow, and third one is my red. So I will get for violet my wavelength would be something in the range of 4000. Then I will move towards the yellow and orange. So my wavelength will go on increasing in this way. So this was my explanation part, and for the practical process or practical how to perform the practical, we will move towards the practical. Thank you so much. Today we will demonstrate the practical on diffraction grating. So in this experiment, the apparatus which we require is a white light source, a collimator, a diffraction grating and a telescope. The main function of the collimator is to focus the beam, and this focused beam is allowed to fall on this prism table, and from this prism table the beam is seen through the telescope. So in this experiment we require a diffraction grating. A diffraction grating is a glass plate which consists of equally spaced opaque and ruling lines. In this diffraction grating we have 15,000 lines per inch, and this collimator focuses the beam on this diffraction grating, and from this telescope we can observe the 7 different colors wavelength or 7 different colors spectrum. The source is the white light source. So white light source consists of 7 colors, which starts from violet and it goes up to red. That is a Vibgyor pattern. So when we will see through this telescope, we will observe a straight, very sharp white light image, and when we shift our telescope towards the left hand side, then we observe, because of the diffraction phenomena, we observe 7 different wavelengths in this practical, which starts from violet and it reaches up to red. Same type of an pattern is observed when we will shift our telescope again towards the right hand side, then same pattern will be observed in this practical. This is basically for the n equal to n order, that is n equal to n order stands for first order grating pattern. Then if we shift our telescope more towards the left hand side, same diffraction pattern of 7 wavelengths will be again seen in this experiment, which we will call it as n equal to second order. But in this n equal to second order, the intensity of the pattern goes on reducing in comparison to n equal to first order. So while performing this experiment, we always prefer for n equal to 1 order rather than n equal to 2 order. N equal to 0 order we don't consider, because n equal to 0 order is our central white light pattern, which consists of all the colors in this pattern. Next, in this experiment we will calculate least count of the apparatus, which is very important in this experiment. Now what is least count? Least count, if we will define that, we call it as a value of one division on the main scale divided by total number of divisions on the vernier scale. So if you see it over here, if I see in this prism table, we have 2 vernier scales over here. This is my V1 and this is my V2. We can consider V1 and V2 accordingly, but whatever V1 we will keep, that V1 will remain throughout as V1 in the whole experiment, even though if I move the telescope towards the left or towards the right. Now we will concentrate on the least count part. So in the least count, we observe here, this is a vernier scale, a smaller scale. Up on the topmost is the vernier scale, and if I see the divisions on the vernier scale, it starts from 0 and it ranges up to 30. That means the total number of divisions on the vernier scale is 30. Then comes my main scale part. If I see the lowermost scale, then I can see it over here. It is starting from 240, then it goes up to 250 and it goes up to 260. That is, there is a difference of 10 degree. But in this 10 degree, we have nearly 20 divisions. So the value of one division comes out to be 0.5 degree, and divided by total number of division, that is 30. So 0.5 degree is my main scale reading, that is the value of one division, and divided by 30 will give me the least count of this apparatus, which is one of the most important part. Then accordingly, we will place for the first reading, I will shift my telescope towards the left hand side and I will place this telescope exactly on the first line, that is the wallet line. As soon as I place this telescope on the wallet line, then with the help of this screw, I will fix the position of this telescope, because while taking the readings from V1 and V2 window, there is a probability that during the process of taking the reading, the position of the telescope can be shifted. So once the telescope is adjusted at a particular line, we will fix this telescope with the help of these screw, and then we will take the readings from the V1 window and simultaneously from the V2 window. Then I will loosen this screw and then I will again place my telescope on the second line. That is, if I take a yellow line, then I will place this telescope exactly on the yellow line. Again, same process, I will fix my telescope and will take the reading from the window V1 and V2. In this telescope, if I see this part, this screw is basically used in order to move my eyepiece to and fro, so that I can get an image very magnified and sharp. Here I have, this is my eyepiece, and in this eyepiece I can see two cross wires, one is horizontal and another is vertical. So we always prefer the horizontal cross wire to exactly coincide with the wavelength or with the pattern which we need to take the reading. So accordingly, I will take the three readings on the left hand side, one for violet, second for yellow, third for red. Then in the second part, I will move back my telescope to the central image, that is the white light image, and then I will rotate my telescope towards the right hand side, and on the right hand side again I will fix my telescope on the violet line. Repeat the same process as I have explained in the left hand side part, and we will take the readings of violet, yellow and red. In this way, once we will take the readings, then we will move for the calculation part. Here we will determine the wavelength of three colors, that is of violet, second of yellow and third is of red. Accordingly, we will go for the calculation part. Thank you.